In this demo, we will use an OpenStack cloud to create virtual network functions, or VNFs, as virtual machines. These VNFs are represented with orange icons in the slide and can include things like deep packet inspection, a local web portal, an advanced firewall, a load balancer, or any other function. These VNFs are connected together by a software-defined networking layer controlled by OpenStack Neutron and presented here with purple icons. The underlying SDN layer provides functions like switching, routing, NAT, or security that help connect and control virtual machines running in the cloud. In this case, the virtual machines we are interconnecting with the SDN layer are the virtual network functions, or VNFs, represented in orange. Outside the cloud, we can see how different residential broadband customers are connected from their homes to the service. Each of these customers has a home device that provides access to the network. In this solution, the SDN layer inside OpenStack is also remotely controlling some network functions that are provided locally in the customer premises, in devices like broadband routers or modems. These network functions from the home network that the customer uses are then enforced locally in the home premises, but they're also controlled remotely from the SDN layer so that they can also be managed, upgraded, and modified. This provides the benefits of a virtual CPE, with the advantage that the home network traffic does not leave the home network except when necessary. Only when the devices connected to the home devices need to reach the internet, the traffic will flow across the CPE device, through the metro network, and into the OpenStack NFV cloud, where it will be processed before being sent out to the internet. Let's now take a look at our demo setup. On the left side of the screen, we can see a standard OpenStack cloud, which we have upgraded with the PLUMgrid plugin for advanced OpenStack networking. We can appreciate this cloud has no tenants configured yet. On the right side, we can see the PLUMgrid console, which provides extended visibility into the cloud and the network service running on it. We can see how one of the nodes currently being controlled by the PLUMgrid plugin is a CPE device connected externally to the OpenStack network. We can use the PLUMgrid console to take a deeper look at the network services running on the device and see how currently there is no traffic running on it. This makes sense as no network services have been programmed in the remotely controlled device yet. The PLUMgrid console also offers additional detail on the OpenStack tenant networks. We can see how no tenants have been created yet. We will see here how all the network services launched in the OpenStack are implemented in PLUMgrid and automatically shown in this window as they are created. We will now launch an automated script that will create the topology of the virtual NFV service. This includes the connectivity to the external internet and an OpenStack tenant dedicated for our NFV application. The OpenStack commands will populate both the SDN network elements and the virtual machines hosting advanced VNFs such as dynamic router and firewall. We will launch another VNF with a web server that will act as captive portal for the users of the broadband service. While the script is running and creating OpenStack services, let's take a look at both consoles to see how services are dynamically created and configured. We can now see a new tenant called NFV being created. If we log into this tenant, we can see how the full network topology of the service is created, including two VNFs as mentioned. On the PLUMgrid console, we can see the detail of the OpenStack network services. Each purple icon on the right corresponds to a network element on the left window. We finally created a network called Metro Network that will be used to aggregate the connections coming from the external CPEs. We will now use some manual procedures to configure PLUMgrid networking parameters that are useful for our service but are currently not supported by OpenStack APIs. PLUMgrid augments the feature set supported by OpenStack Neutron, providing additional networking features that are useful for these use cases. In this case, we will configure the routing protocol OSPF in both OpenStack SDN routers. This will allow them to interoperate with the virtual router VNF depicted in orange, which has been automatically configured with the corresponding parameters, effectively demonstrating how these layers can cohesively work together to provide a combined service. Let's now log into the virtual router VNF and check that the OSPF protocol is running properly between it and the routers running in the SDN layer. We can see how the VNF and SDN routers are effectively talking to each other and successfully exchanging routing information. This allows the entire system to automatically learn about new customers connected to the setup without manual intervention. With this, our cloud NFV setup is complete and ready for onboarding virtual CPE devices into the service. We will now use the PLUMgrid console to manually configure a full home networking service remotely in a CPE device sitting in the customer premises. Our new customer would have received a new CPE device that is configured with the minimum information to be controlled by the cloud. After plugging it into the network and having it onboarded onto the system, this device is ready for an operator to remotely configure any networking services into it. Let's create a new networking service for our CPE customer. We will give this customer an identifier, in this example, the number 253. We can edit the customer effectively, add the CPE wireless LAN port into our virtual setup. This means that all traffic received into the port will be funneled into our network service. We will also add a connector between this home topology and our cloud topology. This connector will transport the traffic between the tenant and the cloud domains. Finally, we will also add a network address translation or a NAT service. This will help the traffic from the different devices at the customer premises to be mapped into a single address assigned to this particular customer. We will now effectively create the virtual topology for this particular tenant with the elements we just added into it. This topology will represent how the home network service works and include all networking elements that will be enforced in the remotely controlled CPE. Let's add the wireless LAN port. Also, let's add a switch to the topology to interconnect the different elements. Home networking devices will need to solve DNS requests, so we will also add a DNS network element. This element could also help us create specific service DNS entries that we map to our own network addresses hosting internal services. We will do that later with our web portal as an example. A home solution also needs a DHCP server. Our DHCP server will offer addresses to the devices in the home network and also inform them dynamically of what gateway and DNS server to use. Our home network will also need a router to connect it to the outside world. This router will be the default gateway of the home devices, so its internal interface will be configured with a private address in the home network. Finally, all these private addresses in the home network will have to be mapped to a single public IP address. This is achieved by adding a NAT element which allows mapping of private addresses to a public IP. When all our home network elements have been configured and deployed, we can connect our virtual CPE to the NFV cloud by using the connector we prepared previously. The connector has one end on the CPE side and another on the NFV side. Once the connector is deployed, both sides can effectively communicate with each other. We connect the NFV side of the connector to the metro network we previously created, so that the traffic can flow through it. Now that the service is ready, it's time to connect some devices to our virtual CPE. Let's take a look at the MAC and host tables from our virtual network elements. The newly connected devices, such as phones or laptops, should now appear here as they get connected to the wireless network port. The devices we just added to the wireless network are now connected. They've also received an IP address from a virtual DHCP server. There is still one configuration piece missing though. As these devices need to learn dynamically how to reach their default gateway and who their DNS server is, we can add these parameters to our DHCP server options so that they're learned dynamically when the device connects. You can also use the physical devices connected via wireless to check connectivity with the home router and the different devices across the topology. The solution is now complete, and we can see how the router can reach its default gateway across the recently connected solution. We are now ready to do some testing. Let's start by checking that both ends of the wire are correctly communicating. We can also send some intense traffic from our terminals and monitor the result. Let's do some high frequency pings across the network and simultaneously send some web traffic. We can use the router in the NFV topology as a snooping device and watch the traffic coming from our wireless device go through our router VNF. This application can be replicated for security and inspection of virtual devices. As a graphical demonstration, let's now watch how a high-definition video stream being watched on one of the devices connected to the CPE is depicted in our traffic monitor graph. We can watch how, as the video stream is turned on, the packet rate is increased, forming a flow between the CPE, the compute host hosting the VNFs, and the gateway representing the exit towards the internet. Finally, let's use a DNS placed in the CPE to implement an internal portal service. We will create a DNS entry called home in our local CPE domain, which we generically call to vCPE.local. When the user accesses the URL home.vcpe.local in their device, they will be redirected to an IP address we choose. In this case, this is the IP we've configured in our internal portal service, so that the user will be redirected to a specifically configured portal hosted in the cloud. Let's log into the web server VM itself and analyze the traffic coming from the customer. As we log into the referred website, we can see how the HTTP traffic is coming into the server. This concludes our demonstration for today. For more information, check us out at www.plumgrid.com. Thank you for watching.